Hello, welcome to a video tutorial for image processing made by Robotics IIT Kharagpur. In this tutorial, we will discuss the topic of noise reduction in image processing. First of all, noise in an image is defined as certain random fluctuations in the brightness or the intensity and color of certain pixels in an image that makes it more difficult to process the image. Basically, it can happen because of certain spikes in the signals that are being sent while the camera is taking the photo, or of course due to atmospheric fluctuations and disturbances that rise while the image is being captured. But what essentially noise does is it makes the image have a lot more extraneous irrelevant information which needs to be reduced for faster and more accurate image processing, and that's what we'll do. This image here shows a good example of what noise can be. Let's zoom in a bit. So it's quite intuitive to understand what the noise here exactly means. It's small granules that make the image harder to observe more clearly. While noise applies to all kinds of images, we will be discussing noise reduction in the sphere of binary or black and white images only, because that's where we shall be requiring it. So one of the major techniques for noise reduction is something that is called erosion and dilation. Now what erosion and dilation first does is it assumes, as should be assumed, that in a binary image, either one of the colors, in this case white, represents the wanted information or the part of the image we are focusing on, and black represents the unwanted information, the information that has to be removed or has to be ignored. So what happens is erosion dilation involves taking a kernel, generally a 3x3 kernel, and taking each kernel of the image rather, and then checking if the majority of that kernel is filled with black or whether it's filled with white. If it's filled with white, then what we do is dilation. We expand the important regions of the image and the white covers the entire kernel, and if it's black, then it's erosion. We remove the small extrusions or the small protuberances of the image and make the entire kernel black. Let's have a look at something here to get a clearer picture of it. So say this is an image which has a good deal of noise with it, and you can see these small granules over here. So on the left, what we have here is this is a kernel highly magnified. So let's suppose, and the border is given red for the sake of clarity, let's suppose this is a kernel, and it so happens that out of these 9 pixels, 5 are black and 4 are white. So in this case, an erosion will take place and the entire kernel will be made black. While if the case is that there are more white pixels than black pixels, then the entire kernel again will be made white. So if you have a look here in this image, say in this area, this is suppose a 3x3 kernel, and the majority of it is white and the minority is black. So then this entire kernel will be made white, so as to reduce the small fluctuations and disturbances in the image. Now this was an image formed by edge detection on a live video feed. You can see there is a good deal of noise here because it was taken by live video feed and because of the distance. Now this corresponding image after as an instance after noise reduction, this is something what it looks like. If you have a look here, there is a large reduction in these small black granules that were appearing in the original image, and that is thanks to noise reduction. Let's contrast it one more time, and yes, that's thanks to noise reduction. So before we move further, let's look at the function. It's a user defined function, noise red. The two parameters are the image and the size of the block, generally 3x3, but we have made it more generic here. Then the various variables required for operation of the function, then a nested loop first which traverses each kernel of the image. That's why the increment is by the size of block and not by 1. And inside this nested loop, inside each kernel, there's another nested loop to traverse the 3x3 kernel, as in the 9 pixels of the kernel. And there, if each individual pixel is examined, if it's white, it's counted in the white counter, and otherwise in the black counter. At the end of this loop, for each kernel, if the number of black pixels is more, then the entire kernel is made black, and vice versa for white. So you've seen how that works. Let's see how this program goes. So here we have the edge detection function, and we have a look at the noise red function. We copy it here, copied, and then this is the main image. And what we do now is after edge detection we run the noise ret function bin, 3. That's our block. So we build this function. What basically it does is it captures the video loaded from file, it applies the edge detection function to the video, and each frame in its which is the binary image, of course, after edge detection, is subject to noise reduction of a kernel of 3. But before we build this, we will do one thing. We'll show you what it looks like without the noise reduction, so you get a better idea of the contrast between the two. So once having built this particular program, we run it. The video used is the same one we've been using for our edge detection tutorial, and in this case, to focus on the noise reduction, we're not showing the original, we're just showing the result. If you have a look here, there's a good deal of noise here, a good deal of small black granules all around the image. It represents the noise, and it's pretty obvious that there is a decent amount of noise here, which would be good to eliminate. So now if we apply this noise reduction function and we build this program, wait for it to be built, and once it's built, we go ahead and we execute it, and now you'll see a marked difference, or at least some difference in the way the edge detection video is being. If you have a look here, you'll find that to some extent the noise has been reduced. The resolution has reduced to an extent because every kernel is now of the same color, but also, and more importantly, the noise of this image has significantly reduced, and has reduced the amount of effort and the amount of extra information we have to process. So that's that, and that's the user defined functions for erosion and dilation. Now in the same way, there are already existing functions in OpenCV for erosion and dilation, and they are very aptly named CV erode and CV dilate. They operate on kernels and can be executed either single or multiple times. For our purpose, of course, it will suffice for us to do it a single time. Let's have a look at the execution and the usage of this function. It's very similar to the main program or the main function of the previous program, except in the case of the noise reduction part, where these the pre-made functions are being called. There are 4 parameters. The first two represent the source and destination images. In this case, the two are same because this function supports what is known as in-place operations on parameters. So the parameter that's taken as the input image can also be given as the output image, because the changes made there are affected on that only. The next parameter is kept null if you want a 3x3 kernel, which is the fact in this case. And the final parameter is the number of iterations we want to do of that act of erosion or dilation. And generally what happens is these two functions are called together, and they're called one after the other so as to perform noise reduction. So let's have a look at how this program works. We'll just copy it in place of both the pre-made noise reduction and the extra program. Yes, so now let's build this and have a look at what CV erode and CV dilate do for the purpose of noise reduction. Right, the program has been built. Let's run it. And you saw just a while ago how the normal noise reduction works. This is how CV erode and CV dilate work. You see there is a noticeable improvement even after the first noise reduction algorithm. It's improved even further, at least to some extent, so that this noise reduction can be taken care of. The basic concept rather for CV erode and CV dilate is similar to what we discussed, because it takes the minimum or the maximum intensity in this values, in this case 0 and 255, and assigns it to the PIC kernel. CV erode and CV dilate, however, unlike our method, can also be used for grayscale intensity images, and they are used, but of course in this case we'll be limiting the discussion to binary images. Had they been used for grayscale images, we would have just explained how it takes the minimum intensity of that particular kernel and or than the maximum intensity and operates with them. Right, so that's CV erode and CV dilate basically. After that we go to what is known as smoothing. Smoothing is also known as blurring. It basically reduces the noise in the image by looking for important patterns and leaving out small fluctuations. This example here shows what smoothing can do to a picture. It reduces the resolution in a systematic manner, and therefore it makes the image easier to process. So there is a well-defined function called CV smooth for the purpose of smoothing of the images. It has several parameters, all of which are necessary, all of which are representative. So the important parameters, of course, are the first few, while the remaining parameters are not so well defined. But what is known is that it is an in-place operation, an in-place function. So the same image can be sent both as source and destination. The third parameter is a macro, which determines basically the kind of smoothing operation we want, or the kind of kernel use, the kind of smoothing operation that is desired. And while there are quite a few macros, CV underscore blur underscore medium underscore bilateral, it is found that CV underscore Gaussian is usually the commonly used one, and usually applicable and effective in most cases. So that's what we've done here. The next parameter represents the size of the kernel they want, which is 3x3, and the last three parameters are not very specifically mentioned, but for our case and for this case in particular, they can be left as 0. So this is the function, or rather this is the program basically that utilizes this function. Let's have a look at how this works. Before we move on to the video, this particular image shows the same image, or a similar image at least to what we were taking before. When subject to CV smoothing, we can see the kind of improvement that is observable in having done something like the CV smoothing. Okay, so now we go to the program and we build upon it. Right, the program is built. We can now proceed, and you can have a look and see the visible improvements that CV smoothing does. I see the small fluctuations that were in this area have almost vanished entirely, and the image looks slightly blurred, but at the same time does look clearer in that sense. And there's a lot of extraneous information that has been removed, and so this is a rather efficient function for smoothing, that is CV smooth, and usage of this can make the task of noise reduction slightly less difficult. So that basically concludes the tutorial on noise reduction. We discussed the basic algorithm for erosion and dilation, as well as the function CV erode and CV dilate, and we had to look at smoothing as well using the macro CV Gaussian and a 3x3 kernel, and the improvements in the overall process. So that is that.